So in this class, we are going to discuss the material selection. Selection of materials depends upon three parameters. One, the availability of the materials, and second, the suitability of materials for the working conditions, and third, the cost of the materials. So these are the important factors on which selection of a material for a particular product depends upon. The knowledge of materials and their properties is of great importance for the design engineer. The machine elements should be made of such materials which has properties suitable for the conditions of operation. In addition to that, the design engineer should be familiar with the effects of manufacturing process and heat treatment on the properties of the materials. So based upon the knowledge of heat treatments, manufacturing processes and material characteristics, what is the outcome the design engineer should have a clear understanding. A tension test is the simplest and the basic tests which determines the values of number of parameters like strength, ductility and toughness. So these things can be understood by the simple tension test. The following information is obtained from the simple tension test. First one, the proportionality limit, and second one, the elastic limit, and third, the modulus of elasticity, next yield strength, ultimate tensile strength, modulus of resilience, modulus of toughness, percentage elongation, and percentage reduction in area. So these are the various parameters which can be obtained from the simple tension test. Here we can see the stress strain diagram for a ductile material. So here from O to P there is a straight line relationship between stress and strain, and there is very close to this point E, the proportionality limit P. E stands for the elastic limit. E is the elastic limit. So that means the stress up to which the member is subjected to, which will comes back after the removal of the load. That means when the load is applied up to the elastic limit, still the member is not going to retain that strain or deformation. Next, the points y1 and y2 are the yield points. So upper yield point y1 and lower yield point y2, these are significant for mild steel, but these are not significant for other materials where simply instead of y1 and y2 we mark only y. So the yield strength is defined as maximum stress at which the marked increase in elongation occurs without increasing the load. So here you can see from y1 to y2 there is no increment in the stress. That means there is no increment in the load, but what happens, there is a increment in the strain. Next, the stress corresponding to U, this is the U point, ultimate tensile strength. The it is the maximum stress that can be reached in a simple tension test. So here is the maximum value of stress that can be reached in the simple tension test. So whereas this point F is the break point, the stress at which the fracture or the separation of the workpiece into two is the point F. Mechanical properties of engineering materials. So the properties like strength, elasticity, plasticity, stiffness, resilience, toughness, malleability, ductility, brittleness, hardness. So these are the main mechanical properties of engineering materials. A particular product may not need all these properties, but some of the products require a combination of these or simply one. So first we start with the strength. Strength is the ability of the material to resist without rupture external forces causing various types of stresses. So when a load is applied on the member, the internal resistance offered by the material is known as stress. So the maximum stress limit the member is going to withstand is known as its strength. Next, elasticity. So this is already we discussed. It is the ability of the material to regain its original shape and size after the deformation when the external forces are removed. So when external forces are removed, if the body is able to come back to its original shape and size, then it comes to its original state. It is by the elasticity. So that is point E shown in the diagram. When the stressing goes beyond the point E, the material cannot comes back to its original state. Next, plasticity. So plasticity is defined as the ability of the material to retain the deformation. Remember, it is to regain the original shape, whereas this is to retain the deformation produced under a load on permanent basis. So this is required in forming operations. In forming operations, we need to retain the deformation, that is a change in dimensions on permanent basis. For that, the property of plasticity is essential. Next, stiffness or rigidity. It is defined as the ability of the material to resist deformation under the action of external load. So here, uh, when the load is applied on the member starts deformation. That is the natural phenomena. But the amount of load needed to cause deformation, if it is more, we say that that member is more stiffer. And on the other hand, if a very small amount of force is needed for deforming the member, then we say it is less stiffer or less rigid. Next, resilience. Resilience is the ability of the material to absorb energy when deformed elastically and to release this energy when unloaded. This is very important. So resilience is the amount of energy absorbed by the material within the elastic limit. So up to elastic limit, if you are stretching the member is going to absorb the energy. When you release that load, then the energy is dissipated and member comes back to its original state. So the amount of energy absorbed by the member up to the point of elastic limit is known as resilience. Whereas toughness is defined as the ability of the material to absorb energy, just as here, but the difference comes before fracture takes place. So there is a difference between resilience and toughness. Resilience is the loading of the material up to elastic limit, whereas here the loading of the material is up to the fracture or separation takes place. Here the energy stored within elastic limit, here the energy stored up to the fracture. So toughness is the energy for failure by fracture. So here in these two plots we can see uh, up to elastic limit, if you strain the member is going to store this much of energy, and this energy is known as the resilience, and within this the shaded area is the modulus of resilience. And when you come to the second plot here, this is the break point or separation. So until the break point, the amount of energy stored by the material is known as modulus of toughness. This is modulus of resilience. Next, the term malleability. As we know, malleability comes from the word mallet, that is hammer. So it is the ability of the material to be hammered into thin sections. Next, ductility. Ductility is defined as the ability of the material to deform to greater extent before the sign of crack when it is subjected to tensile force. When the member is subjected to a tensile force, if it has extended or deformed by greater extent, there must be lot of deformation. So that is the material, ductile material. So brittleness. So this is the opposite of ductility. This is the property by which the member shows negligible plastic deformation before fracture takes place. So a ductile member shows appreciable or lot of deformation before the sign of crack or failure, whereas brittleness, on the other hand, it shows very small or negligible plastic deformation before fracture. Next, hardness. So hardness is the ability of the material to resist the indentation or scratching, or it is also known as the penetration or permanent deformation. This is very essential for the products or elements which are in the relative motion. So let us look at the various most commonly used engineering materials. So first one is the cast iron. Cast iron is an alloy of iron and carbon containing more than 2% of the carbon. If carbon percentage is more than 2, between 2 and 4%, it is the cast iron. So from the design considerations, the cast iron offers the following advantages. So what are the advantages? It is available in large quantities. So this is the one of the three significant or important parameters, the availability of the material. So therefore, when it is available in large quantities, by using the cast iron, we can make the products on mass scale. And another important thing is the tooling required for the casting process is relatively very simple as well as inexpensive. Next, the cast iron components can be given any complex shape. So it doesn't need any costly machining operations. The complex shapes can be obtained by simple casting with inexpensive tools. So cast iron has very good compressive strength. The compressive strength of the cast iron is 3 to 5 times that of the steel. Remember, this is very, very important uh, for the cast iron. This is advantageous in several applications. Cast iron has excellent ability to damp vibration. That means it is going to absorb the vibrations. So therefore, it becomes an ideal choice for the machine tool guides and frames. So lathe bed or any machine tool bed or guides are made of cast iron. So the reason is it is going to absorb the vibrations. It is going to damp, that means reduce those vibrations. Next, cast iron has more resistance to wear because the percentage of carbon is more, it has greater hardness. When it is having the greater hardness, it does have greater wear resistance. The mechanical properties of cast iron parts do not change between room temperature and 350. So up to 350 degrees centigrade, it is going to retain its mechanical properties. The cast iron parts have low notch sensitivity. Even when there are certain changes in cross section for the cast iron products, they are not going to be affected by those changes in cross sections. Maybe holes or maybe keyways or whatever it is. So those are called notches. So due to the presence of a notch, its sensitivity to the notch is very low. Alloy cast iron. So by adding nickel, chromium, molybdenum, copper, manganese in sufficient quantities, alloy cast iron can be produced. This alloy cast iron has some improved properties over the ordinary cast iron. They are increased strength, high wear resistance, and corrosion resistance as well as heat resistance. These are all there for the cast iron, but they are improved by adding the one or more of these elements, so which improves the one of these properties based upon the type of element it is added. The alloy cast irons are extensively used for gears, automobile parts like cylinders, pistons, piston rings, crankcases, crankshafts, camshafts, sprockets, wheels, pulleys, brake drums, shoes, parts of crushing and grinding machinery. So, uh, when the ordinary cast iron has several limitations, the alloy cast iron has improved such conditions. That means the limitations are extended. That means limitations are minimized and strength is improved in various parameters, like mechanical properties. So those elevated mechanical properties increases the use of cast iron for the above mentioned components. Now let us move to steels. Steels are having carbon percentage between 0.15 to 1.5. So when carbon percentage is less than 0.15%, it is called the dead mild steel. And the most commonly used engineering material is low carbon or mild steel. It is having a carbon percentage between 0.15 to 0.45%. And next is medium carbon steel. So medium carbon steel is also used as a, for shafts, gear wheels, etc. And it is having a percentage of 0.45 to 0.8%. And high carbon steel, these are used for cutting materials, and its carbon percentage is starting from 0.5 to 1.5%. So here we will be focusing on high speed steels. So these are the few of the high speed steels, and these are used for mostly the cutting tools. So first starting with the 1841 high speed steel. So here 18% is tungsten, 4% is chromium, and 1% is vanadium. So it is one of the best all-purpose tool steels. It is widely used for drills and lathe tool bits, planers and shaper tools, milling cutters, reamers, broaches, threading dies, punches, etc. For most of the general purpose applications, we use 1841 high speed steel for the tools. Next, molybdenum high speed steel. So in this steel you have 6% tungsten and 6% molybdenum, 4% chromium, 2% vanadium. It has excellent toughness and cutting ability. So the you add addition of molybdenum increases uh, its usage for drilling and tapping operations. So when compared to the 1841, the molybdenum is relatively cheaper. Next, super high speed steel. Here, this steel is so called because cobalt, addition of cobalt. So in this cobalt is between 2 to 15%, which increases the cutting efficiency at elevated temperatures. On the average, it contains 20% tungsten, 4% chromium, 2% vanadium, 12% cobalt. Since the cost of the steel is more, because you can see here in this first one there is 18% tungsten, here there is 6% tungsten, here it is 20% tungsten. So the tungsten is a costly material. When you add tungsten, the cost is also going to add, and this is as the name suggests, it is super high speed steel. This is principally used for heavy cutting, which imposes high pressure and temperatures are very high on the tool. The nomenclature here. XT75W 18 CR4 V1. So it means it's a tool steel where average percent of the carbon is 0.75%, and tungsten, W stands for tungsten, that is 18%, Cr stands for chromium, that is 4%, and vanadium 1%. Next, let us go for the material used for springs. So, in engineering parlance, the steels which are used to make springs, also known as spring steels, based upon the composition, they may be called as different with different other names. The most suitable materials for springs are those which can store maximum amount of energy in a given weight or volume of the spring material. For the given weight or volume of the spring material, if the member can store maximum energy, that is the most suitable material for spring. And these should have high elastic limit as well as high deflection value. So examples are high carbon steel. So as we have the earlier discussion, the steels having up to 1.1% carbon and addition of 0.2 to 0.5% silicon and 0.6 to 1% manganese. So these makes high carbon steels for springs, and these steels are used for laminated. Laminated springs means the springs which are like this. So several plates put over one over the other, and so load is applied here, and this is placed on the axle. So when the load is applied, they will be deflected like this. So thereby it is absorbing energy. When load is taken off, and they comes back to its original state. So laminated means uh, several plates placed one over the other. So high carbon steels of this magnitude or this composition is used as laminated springs for locomotives, carriages, wagons, heavy road vehicles like trucks, etc., buses. Chrome vanadium steel. These are high quality spring steels, contains 0.45 to 0.55% carbon, 0.9 to 1.2% chromium, and 0.15 to 0.2% vanadium, 0.3 to 0.5% silicon, and 0.5 to 0.8% manganese. These steels are used for motor car laminated and coil springs for suspension of the automobile, and they are also used for aircraft valve springs. So these are very high quality, these are also very costly, and they are used in premium automobiles as well as in the aircraft engine springs. Next, silicon manganese steel. These contains 1.8 to 2% silicon and 0.5% carbon and 0.8 to 1% manganese, and these have high fatigue strength, resistance, and toughness. So we have seen starting from cast iron and the several steels, the necessity of heat treatment and the effects of heat treatment of the steel. Let us discuss in this slide. The aim of the heat treatment is to achieve one or more of the following objectives. Number one, to increase the hardness. Number two, to relieve the stresses. And number three, to improve the machinability. Number four, to soften the metal. Number five, to modify the structure to improve the electrical and magnetic properties. Number six, to change the grain size. Number seven, to increase the qualities of the metal to provide better resistance to heat, corrosion, and wear. So these are the various objectives of conducting heat treatment on the steels. Uh, Same product may not require all these objectives, and it may require one or two or some of these objectives to be met. So depending upon the type of objective needed for a product, we will choose the heat treatment process. So normalizing. In this process, homogeneous structure is obtained, which provides higher yield point, ultimate tensile strength and impact strength with lower ductility to the steels. So when you do normalizing, the heat treatment normalizing, so it gives the homogeneous structure to the material. So when it gives homogeneous structure, it improves the yield strength and tensile strength as well as the impact strength. Next, annealing. So here we have two types of annealing. One is full annealing and another is process annealing. The purpose of full annealing is to soften the metal, to refine the grain structure, to relieve the stresses, to remove the trapped gases in the metal. So the purpose of full annealing is to soften the metal. The hardened metal is softened by the change in the grain structure. The grain structure changes, the metal becomes either hard or soft. And also this is done to relieve the stresses due to the cold working process or hot working process. Residual stresses are left in the material, and during the process some gases are trapped inside the material. So these are all relieved by the process called full annealing. Next, process annealing. The process annealing is used for relieving the internal stresses set up in the material and for increasing the machinability. So here we are softening and we are relieving the stresses and also removing the trapped gases, whereas here we are relieving the stresses like as the before, and also we are increasing the machinability of the steel. So this is called process annealing. Next, hardening. This is another heat treatment process. The objective of hardening is to increase the hardness. As the name suggests, when we do the hardening heat treatment, so the member will become more harder. So when it becomes more harder, what it can do? It is going to resist the wear. Wear resistance increases. And when it becomes harder, it will be used as a cutting tool. When it's more harder, it can be used as a cutting tool. Next, tempering. The steel is hardened by rapid quenching, is very hard and brittle. So when the steel is rapidly quenched, it becomes hard and brittle. So therefore, it contains internal stresses which are very severe and unequally distributed. They cause cracks or even rupture of the hardened steel. So therefore, we perform tempering on these rapidly quenched steels. So the objective or the reasons for that is to reduce the brittleness of the hardened steel, and it increases the ductility, to remove the internal stresses which are caused by the rapid cooling, to make steel tough to resist shock and fatigue. So the purpose of tempering is not only to reduce the brittleness due to hardness and increasing the ductility, and not only increasing the removing the stresses due to rapid cooling, and the most important thing is it is to make the member tough. When it is tough, it is going to resist the shock and fatigue. Next, surface hardening or case hardening. So some of the members required a hardened surface, but the interior need not be that hard. The examples are shafts. So in the shaft, you should have the exterior surface hardened, and therefore in for such requirements we will go for surface hardening. This hardened surface is going to resist the wear and tear. That means wear as well as tear. That means some cracks appearance. The core is soft, and this is going to absorb the shocks. When the core is soft, it is going to absorb the shocks. When surface is hard,